Okay, so I got a vise here. Okay, um, I'm pushing with 300 newtons on that handle to cause a torque on that thing to tighten this thing down. Okay, it gives me the diameter of the screw, the lead, which is the um, displacement or the distance between threads, and then the coefficient of static friction on the screw. So here's what I know. I know the moment necessary to to clamp this, to tighten this down. The tightening moment is RW tangent of the lead angle plus the friction angle. So before I move on and talk about each of these, this is the equation I use. This is for tightening, okay? Maybe I just go ahead and say M tighten. Okay, you get a different one if you're trying to loosen a screw. Okay, tightening, you add the two together. Okay, and by tightening, I mean tighten it down, or however the screw is working, right? So in the book they give an example of lifting like a screw jack. Okay, that is essentially working against the force, right? So tightening, working against the load, that sort of a thing. Okay. Now, W, again, they always talk about this with regards to like a screw jack. W is force through the screw. So force in the screw. Okay. Which doesn't make sense to be a weight when again this thing's horizontal, but it's the force going through that screw, and I need to figure out the moment necessary to tighten it down. Okay, so the first thing we do with these screw problems is go ahead and find um, your angles. Okay, now my lead angle is just going to be the inverse tangent of the lead distance divided by essentially the circumference, because this is just a inclined plane wrapped around a screw. So the lead is the height of that, circumference is the length of that. Okay, so I can go ahead and plug in all of my values here, where the lead is 25, the diameter, okay, which is why I get 2r, right? So it's going to be 25 pi. Again, just giving me that circumference. So the lead angle is 5.45 degrees. The friction angle is just the inverse tangent of mu s, which for this is 0.25. Doing that inverse, I get 14.04. Okay, so because that friction angle is bigger than the lead angle, okay, it's sticky, it's self-locking, which is good. Okay, when I let go, it'll stay stuck where it is. It won't unravel, so to speak. Okay, call that self-locking as long as the friction angle is bigger than the lead angle, which is the case here. Now, my moment, okay, is just going to be 100 times, that's the moment I'm applying at the end there, that 30 newtons, 100 millimeters away. That's going to be a 3,000 Newton millimeter moment. So I'll use that 3,000. Okay, set that equal to R, which is going to be 12 and a half. It's going to be half the diameter, times W, which is the force in the screw. That will be the clamping force, right? As I clamp that down, I'll create that force in the screw, times the tangent of 5.45 plus 14.04. Okay, and doing that, I get a W equal to 678 newtons. Okay, so mechanical advantage on this one is great. I've only applied 30 newtons of force, and I get out 680 newtons of clamping force. So large mechanical advantage. Again, W is the force through the screw. For tightening it down or lifting it, working against the load, okay, you add the two angles together that you find there, and then solve the equation, which is not a difficult equation once you know how to set it up for the process that you're in fact looking at.